Hello everybody, happy Thursday, and welcome to Lecture 9. So we'll do a brief review from last lecture. We talked about factors that inhibit tropical cyclone formation. So it's the opposite of the 6 ingredients for tropical cyclone formation. We talked about tropical cyclone basins and what each of the tropical cyclones are called in the basins, like when they become hurricane strength. So we have typhoons, hurricanes, and cyclones, but it's just 3 different words for the same thing. We talked about hurricane forecasts from the National Hurricane Center in Miami, and we talked about the cone of uncertainty, and we talked about the eye wall, and spiral rain bands. So let's talk about some of the damage. One of the main things that causes damage from tropical storms is storm surge. So the strong tropical cyclone winds can also push large volumes of seawater to the shore, and this causes coastal floods, which are called storm surges. And storm surge kind of works more like a bathtub. So the water levels start rising and it gradually breaks the barrier to whatever city you have, and it can cause roadways to flood and significant damage. Storm surge is enhanced by the low pressure center in the eye, and the low pressure center causes the sea level to bulge upwards, and it raises the sea level even further. So here's a video if you want to check it out. Storm surge is interesting to measure. They usually measure it after the fact, and the way that they do that is they go and check for damage, and they see how high the damage is. So, like for instance, Hurricane Katrina in Mississippi, my grandparents lived in Biloxi, and I went right after Katrina. I went out there in August, and it was, oh my gosh, it was unlike anything I've ever seen. It was so badly damaged from the storm surge. Just, there's a lot of casinos on the water in Mississippi, and like, I mean, you could see the first floor carpets of some of the bigger casinos because they just toppled over. But the way that they measured the storm surge was people would get out in boats and they would go out to the trees or like a bridge, and they would like cut an area of the tree to mark where the storm surge was up to, or they would like mark an area of the bridge, and the storm surge in Katrina got up to like 26 feet. So where the sea level is normally 0 had 26 feet of water. It's pretty significant. So yeah, storm surge is an abnormal rise in sea level above and beyond the rise predicted by astronomical tides. So that's caused by the winds and the low pressure in a tropical cyclone. So normally the tides are pulled inwards and outwards by the moon, and it's very predictable. But when you have a tropical cyclone that's piling water up on top of, like, up into a pile, basically, it can create significant flooding. And this is the most dangerous part of tropical cyclones, because it causes rapid and extreme coastal flooding. So yeah, this is the main reason why you want to evacuate during a storm. Like, the winds are bad, of course. Like, you don't want to be in 100-mile-per-hour sustained wind. But storm surge and flooding and stuff is what will have you up on your roof. So even weak Category 1 hurricanes and tropical storms and post-tropical storms can produce these storm surges. And if the area you're staying in is prone to flooding, like, just leave. Like, get out. Don't stay. Okay, so here is the regions of the tropical cyclone. So storm winds are combined winds due to both the rotation and the forward speed of the cyclone. Okay, so you have the overall storm motion. That's the forward speed. So the storm is advancing. On the right side, you have rotating winds in the same direction as forward motion, and the storm winds are the strongest on the right. And then on the left, the winds are rotating in the opposite direction, and the storm winds are weakest. So also, if you think about it, when the storm is rotating, especially when it's going over land, when it starts to go over land, on the right, it's pulling in all this water. It's pulling it north. And it has increased motion from the forward speed, like these combine. On the left, or the west side of the storm, the winds are rotating the opposite direction than the forward speed, so you subtract the forward speed from the wind speed. And it's pushing the water away from, like, it has all this time. The wind is spiraling around, and when it goes over land, it slows down. So the wind speed on this side of the storm is going to be slower. So the most dangerous part of the cyclone you can be on is the right-hand side. This is usually the case. What happened in Hurricane Katrina that was so bad was you had something that looked like this, and it was going over the land. And for a while, everybody was like, oh, Louisiana is saved. Woohoo! Yay! They're on the left-hand side of the storm. But what ended up happening was Katrina made landfall, and you had Lake Pontchartrain, which is like, let's say like New Orleans is down here, and Lake Pontchartrain is up here. It's huge, by the way. I don't know if y'all have ever been over Lake Pontchartrain. It's like driving over the ocean. It is gigantic. This wind here picked up Lake Pontchartrain water, and it dumped it over New Orleans. So it moved water from the north towards the south. And that's why it was kind of unexpected for such damage to happen. The levees broke because it's not used to that motion, and the levees weren't built properly. They were not built tall enough. And it caused really severe damage that was unexpected because it didn't pull in Gulf water, it pulled in Lake Pontchartrain water. So, not always a good thing. Not good to be on a bay when you have a hurricane. But typically the region that gets hit the worst is the right side. So, the bigger the storm surge, it's created by a faster rotation and a faster forward speed. So if you can get the storm to rotate faster and the speed to be faster, you're going to have a bigger storm surge. So, here's the infographic. So imagine this again. So it's rotating counterclockwise. Now look at this. So this is Lake Pontchartrain right here. And the hurricane came through, and it was rotating like this, Hurricane Katrina. And so, it was on the left-hand side of this storm. So they thought it was going to be okay. Because New Orleans is relatively inland. But it ended up picking up this water from Lake Pontchartrain and dumping it over New Orleans. So that was a total fail. That really sucked. But Biloxi is right here. That's where I said my grandparents were from. And it was on the right-hand side of the storm, and everything was just so messed up. Like, unbelievable damage. My grandparents, their house was the only house left standing on their street. And by some miracle, all they did was get a little flooding and lose their shingles. But there were 6 people in their neighborhood that did not evacuate, and all of them died. So it's just horrible. Like, don't take risks with hurricanes. Don't have a hurricane party. Leave. Do not stay. Exit the region. Don't risk it. So, more on storm surge. Storm surges are enhanced by narrow places like inlets, bays, and rivers. So I kind of talked about this earlier in the semester. So you have like large volumes of water in tiny spaces, and so the sea level rise more in like bays than they do in other places. Like if you have this bay here, the volume of water can increase very rapidly. And it's confined in this small space, so there's not really much like area to disperse it. So it can overtop its banks really easily. And also, the Gulf of Mexico is prone to storm surge because of the large volumes of water. So again, this is this concave coastline, and the water just kind of like piles up. And so places where you can get it the worst are in these bays that also are like they're like ultra concave, right? So they really pile up. So the Galveston Bay, the Aransas Bay, I don't know where that is. Matagorda Bay, Vermilion Bay, Lake Borgne. I'm assuming it's like these. And then Lake Pontchartrain. I still don't know how to spell this word. I always misspell it when I'm trying to spell it. Florida is also highly susceptible to flooding for the same reasons. Yeah, so I used to live over in Niceville, Florida, and you can't see it. This is the Mobile Bay. It also floods out pretty easily and floods into Mobile. But there is a bay called the Choctawhatchee Bay that also floods out pretty easily. Yeah, here's the Choctawhatchee Bay, like right here. And this is like the Pensacola Bay. These all flood out. This is where I used to live. Right here. Do you care? And this is also where I used to live, like right here. And this is where my grandparents live. Do you care? Okay, I shouldn't ask that. Oh, look at this. New Orleans is like completely underwater. That's not good. That's not good. I have a lot of friends that live in Louisiana and this Mississippi area. Is this like a storm surge map? This is okay, the light blue areas is areas at or below 10 meters above sea level. Okay, yeah, leave if you're in this region. Exit, go north. Do not be here if there's a hurricane. Exit. So storm surge is enhanced along coasts with flat topography. Last night I was watching a Vsauce video. Apparently Florida is the flattest state. Did y'all know that? I thought it was Kansas, but Kansas is the 7th flattest state. Florida is the flattest state. And also, if you look at the Earth from space, the entire thing is flatter than a pancake, which is yeah. Yep, okay. Anyway. But locally, topography matters, and if you have a place that's below sea level, like, it's gonna be prone to flooding. So water can travel further inland. In places in Florida, there are, like, most of Florida is, 100 feet above sea level or less. Like, there's only a change in elevation of 100 feet. So, yeah, it cut it off, but a lot of Florida is pretty close to sea level. Yeah, so storm surge is enhanced on coasts that are at or below sea level. So water has to rise less to have a serious impact on these places. I'm pretty sure that New Orleans is 13 feet below sea level or something like that. I don't know, that's what they taught me in class. It's like really, really not a good situation. New Orleans is right here. Okay. Here's the storm surge forecast for Hurricane Harvey. So the max value was 13 feet, about right here. So, yeah, wherever the coast is, like where it normally is, where it's 0 feet of water, now you have 13 feet of water. So if you think about it, That means that everywhere that is less than 13 feet above sea level is going to be underwater. So if all of this area right here is 13 feet above sea level, it's all going to be flooded out. It's not just like 13 feet inland. It's like everywhere that's 13 feet above sea level or less is going to be flooded. Not good. Okay. Evacuation. Very good. Evacuation is good. Oftentimes, before a large hurricane hits, state officials will call for an evacuation. It can be recommended voluntary evacuation or ordered mandatory evacuation. In a mandatory evacuation, they can't force you to leave, but they will cut off all your services if you do not leave. Okay, so leave. If you are in a forced evacuation, even if you're not, like if you're in a voluntary evacuation, I suggest that you probably leave as well, because somebody very smart issued the voluntary evacuation. Anytime they circle your county and they say evacuation, you should probably leave. But if it's mandatory evacuation, don't stay, because you're not going to have any power or running water, and it could be weeks before you get that. That was like the main problem with my dad when he stayed in Hurricane Michael. He didn't have power for weeks, and that was not good. Like, his phone died, and I was very worried. But he's fine, but, you know, like, evacuate, I don't know. If there's gonna be a big hurricane, like, leave. Reminder, the ability to evacuate is often tied up with privilege. This is true. You know, the South, a lot of people are poor in the South, and they can't afford to evacuate. Gas prices are really high right now. A lot of people don't have cars, so a lot of people don't have that option. It's really unfortunate. But if you're able to evacuate and you know someone who doesn't have the means to, help them out and help them evacuate if they need to. And also, staying in a hotel is tough. Hotels become more expensive. Hotels become booked up very quickly. And so, like, the further you wait, the harder it is and the farther you have to travel. So, like, for instance, like, I used to live in Hattiesburg, Mississippi, which is about an hour north of the coast, and all of those hotels would get booked up, like, almost instantly. So people would have to travel farther and farther to get away from the storms. The Waffle House Index. I love Waffle House. I don't know anybody who loves Waffle House. That's currently my friend here in Oklahoma, which is really sad because, I don't know, I spent many a great hours in the Waffle House. And the Waffle House Index is a real thing used by FEMA. There's a permalink to prove it. The government uses the number of Waffle Houses that are closed in an area to determine how bad a natural disaster is. So Waffle Houses don't really close. Like, they rarely close. So there's 3 levels. So green they're serving the full menu. The restaurant has power, and damage is limited, or there's no damage at all. So, did y'all know that Waffle House has a secret menu? Just ask for their, like, full menu. Like, they give you the menu with all the pictures on it, but that's not the full menu. If you ask them for the full menu, they'll, like, give you, like, a more advanced menu. Yellow, they have a limited menu. No power, or only power from a generator, or food supplies may be low. Okay, no all-star special with the yellow. And then red, the restaurant is closed, indicating severe damage or severe flooding. So, I don't know how they get people to go to work. Anyway, yeah, if the Waffle House is closed, you know something's wrong. So, here's the most important points from the tropical cyclones lecture. There's 3 types of tropical cyclones. And there are tropical depressions, tropical storms, and hurricanes, and there's wind thresholds for each of them. There's 6 ingredients for tropical cyclone formation. There are also factors that inhibit or prevent tropical cyclone formation. The National Hurricane Center makes hurricane forecasts that you can easily access on their website. Tropical cyclone has smaller scale features embedded within, including the eye, which is the area where there's no weather, the eye wall, where the weather is most severe, and then the outer rain bands, where the tornadoes form and you have a combination of rising and sinking motion. Rising motion within the band and sinking motion outside the band. And then we talked about storm surge and how it is less or more impactful depending on what side of the hurricane you're on. So if you're on the eastern side or the right-hand side of the hurricane, the storm surge is going to be more impactful because it doesn't have the friction from the land. It has that forward motion of the storm to combine with the wind speed of the counterclockwise rotation. So you get enhanced wind speeds on the right-hand side of the storm. And, okay, that's it for day one, or not day one, PowerPoint one. Sorry, these are labeled for people that go to school for a whole semester. We have to do a little bit more in this class. Okay, so the next PowerPoint. Okay, I just went over this, so I won't go over this again. Now we're going to talk about weather radar. So, radar means radio detection and ranging. And it's become so common, we just call them radars, and it's not an acronym anymore, it's just a word. So, it's this device here, and at this little point, it transmits a pulse of energy, electromagnetic energy, specifically microwaves, and they're sent out in a specific direction. And what happens is these microwaves hit something, so raindrops, etc. And some of it is scattered back to the radar. So I wish I had like more space, but you know, if there's like a cloud right here, it's going to hit the cloud, and then that cloud is going to reflect some of this radiation back to the radar, and it detects how much and the distance. So it takes into account the speed of light, and so it can tell how far away it is and how dense it is based on how much electromagnetic radiation is reflected back and how long it takes. So it gives us information about the size, shape, composition, orientation, and velocity of particles. Okay, here's the little radar. Yeah. So step one. Okay, reflectivity. This is a word for how reflective something is. And we look at reflectivity, that's like your basic radar function. So, you know, when you have like green, yellow, red, purple, and it shows how much rain there is, or like the precipitation, that's reflectivity. So it's just bouncing this microwave beam onto these particles, and then it's bouncing back towards the radar to measure it. So the radar dish emits a beam of microwave energy in pulses. So yeah, it's pulses. It doesn't like constantly emit it, it like lets out a pulse. And it encounters this precipitation as it travels through space. We have a gigantic raindrop. It's going to be really unfortunate who's under that, you know. Okay. So then the second thing that happens is precipitation scatters on a portion of energy. Precipitation scatters a portion of the energy from the radar beam in all directions. So yeah, the beam hits it. Some of it moves back towards the radar, but it's scattered in all directions. And this is called the radar echo, or the echo. So this is the echo, so whatever comes back at it. The energy the echo returns to the radar is collected by the dish, and it measures how much energy there is and how far away it is. and then it will emit another beam, and the process starts over. So the reason why it emits in pulses is because it has to know how far it went, and like it waits for the return energy to tell how long it took for the beam to come back. And if it was constantly emitting, it wouldn't know like how long it took. It would be a little difficult to tell where things were. So it has to like send the pulse out and wait for the energy to be collected again before it sends out another pulse. Also, it's in like a golf ball and it's spinning really fast and it's letting out pulses in all directions. Yeah. So it doesn't emit. It emits energy not continuously, but in discrete pulses. So it allows the radar to listen for returns. So there's a set amount of time between pulses called pulse repetition time. So typically that's 1 millisecond. And then they use this symbol tau, which just looks like a T, and that's the duration of the pulse. I don't know what a US is. Typically, I think that's supposed to be micro. So yeah, 1 microsecond for each pulse. So it lets out a pulse every microsecond. So that's 10 to the negative 6 seconds. The time between pulses is when the radar listens for echoes from precipitation. So the time spent listening and waiting for like the energy to return is much greater than the time spent emitting the pulses. Yeah, so it quickly emits a pulse and then it waits this amount of time for it to come back, and then it emits another pulse and then it waits. So it sends a beam out and it waits for it to come back before it emits another pulse. So it can determine how far the particles are from the radar by how long it takes the scattered energy to return. So if it takes a longer amount of time, the particle is farther away, because this energy, this microwave energy, travels at the speed of light. So they can take that into account and measure exactly how far away the pulse is based on how long it takes for it to return. And if it takes longer to return, that means that it is farther away. There's also a maximum range that particles can be sampled by the radar. So here is the formula for the maximum radius. So it's the speed of light times the pulse repetition time over 2. Someone smart came up with that, not me. This is the farthest a particle can be for its echo to arrive before the next pulse is sent out. And particles past this distance can cause huge problems in radars. Yeah, so like a lot of places in the United States, especially in like mountainous areas and stuff, just don't have that good of radar coverage. And it's a problem because these areas just, you can't really see what's going on. You have to infer. Also, as you can see, the farther away, like there's a tilt angle. So the farther away you get from the radar site, the higher up in the atmosphere it is. So you can't really see down near the surface the farther out you get, unfortunately. Anyway, about this particle size, so larger particles, so like big raindrops or hail, will scatter more energy. So yeah, if it's like a small particle, a lot of energy will be just passed through it, but if it's large, it's going to reflect a lot more energy. So however much energy is returned will tell us about the particle size. Hail scatters the most energy, especially wet hail. Like if you get wet hail, it's going to look crazy on the radar. And then rain, and then snow. And so the returned energy tells us about the particle composition. So yeah, usually if you have like super high reflectivity, you've got like either a lot of rain, really big raindrops, or you've got hail. So the more precipitation in a given volume of the atmosphere, the more energy is returned. Yeah, so it doesn't just scan like individual particles; it will like scan like a cubic area of volume to see how much is returned within this volume. So how do we tell if high return energy means a lot of particles, large particles, or hail or rain? We don't. I mean, we can, and I'm sure they'll go over this in your future classes. But yeah, you can kind of infer based on what type of storm it is. Like, if it's super high and it's in a supercell, you're probably just going to assume that it's hail. Yeah. Hail also has like, sometimes it will create, like, a false echo behind it. I don't think we get into that. Okay, so how the radar works. So reflectivity. So we have the energy returned, and it's called dBz. I don't remember what this stands for, but like this at the bottom, these like different colors, these colors right here, these are different dBz's. So and they have a color scheme. So this over here, like these colors are higher dBz's. So like these orange and red colors in the storm, it's gonna rain harder. It's got higher values of dBz, and like the green portion have lower values of dBz's, so they don't have as much rain in these areas and less return energy. This is the typical color scheme used by all meteorologists. So blues are usually for snow and the edges of the rain echoes. So yeah, you can see around the echoes, there's kind of like a little blue layer. So not too heavy. Then the greens, like here, and also kind of a little bit closer to the echoes, it's light precipitation. These yellow regions is moderate precipitation. And then the reds, they're heavy precipitation or small hail. And then if you can get into the pinks or purples and even the whites, you have very intense rain, but possibly severe hail. Doppler radars are able to approximately measure how quickly targets are moving to or from the radar. So, yeah, it was very difficult to understand at first. It makes sense to me now, but the velocity, there's a lot of like kerneling and smoothing because there's some problems with velocities and its detection by the radar. But what happens at a very basic level is it sends out two pulses. So it'll send out its first pulse and it will see where it is, and then it will send out a second pulse and it will see how far it is there, and then it will check the difference between the first pulse and the second pulse to see how far it moved. And it will just calculate how quickly it's moving just based on two different pulses that it sends out. And yeah, you need two separate pulses to determine the velocity. Yeah, you don't have to learn the details of radar in this class. I'm sure you'll learn about it in other classes, especially if you take a radar class or an instrumentation class. I highly recommend it. Using the radar is probably the best thing I've gotten out of meteorology, because you can like see tornadoes and stuff. This is also how police radar guns work. So yeah, they'll like a police radar gun, they'll send out the first pulse to your car, and then they'll send out a second pulse to your car just to see how like far away it was and how close it got, and like the distance difference. They can calculate how fast you're moving. So there's radial velocity. So radial velocity, you can kind of think of it like if you had a circle. Like, okay, this is not a raindrop right now, like this is just like a circle. The radial velocity is like the velocity like moving to or from the center of the circle. Like, it's not moving this way, it's moving like to and from the center of the circle. So like in straight lines coming out of the circle. Like these two arrows are kind of like radial velocity. because they're pointed towards the center of the circle. So, yeah, this is the component of precipitation's motion toward or away from the radar dish. Since precipitation particles are advected by the wind, the radial velocity gives an estimation of wind speed in knots. It's not the actual wind speed, so radial velocity is the approximate wind speed of the component of wind directed either toward or away from the radar dish. So yeah, you can have components of wind that are moving like in a different direction of the radar dish, and the radar can't really calculate that. It can only calculate how fast it's moving toward or away from the radar. The component of the wind moving perpendicular to the radar beam is not measured. And so the ones that can determine how fast a particle is moving toward or away from the radar are called Doppler radars. And that's typically what we use. Here's a video on the Doppler effect. It's 51 seconds long if you are interested in that. Okay, so this is like the velocity scan. So this is, if you get an app like RadarScope or something, you can see all of these different tabs. So they have like the velocity. You can click like storm relative velocity. So green means that the wind is directed towards the radar. So this is the radar site, and remember we're thinking about this radially. So if it's green, it means that the wind is incoming towards the radar. And if it's red, it means it's directed away from the radar. So we can just kind of assume that this wind speed here is kind of southwesterly, like it's coming from here and it's moving towards here because it's going towards the radar, and it hits the radar site, and now it's moving away from the radar. And it's moving away from the radar here too. Yeah, so, I mean, south to north, more or less. Yeah, so we must know the radar's location in order to use radial velocity correctly. This is true, because you have to know where it is outgoing and where it is incoming from. The brighter the color, the higher the wind speed. And what is the wind direction in this example? It's southerly. So, going towards the radar, going away from the radar. Yeah, southwesterly. So, the wind is directed towards the radar in the green. It's also directed towards the radar here, but it's just the component of wind that's going towards the radar. So this wind may be moving like differently, but we can't detect if the wind is going this way. We can only detect it in the radial direction. And then red means the wind is directed away from the radar. Yeah. Okay. This is a terrible combination for colorblind individuals. I guess she replaced green with blue. So, blue means the wind is directed towards the radar, and red means it's directed away from the radar. Okay. That's nice of her. That's good. Unless you're blue colorblind, then that sucks. But I'm pretty sure most people are red-green colorblind, so hopefully you're not blue colorblind. So, what is the wind direction on this velocity plot? So, blue means the wind is directed towards the radar, and red means the wind is directed away from the radar. And remember, it's strongest where it's the brightest. So, this is the brightest area. And, it's going towards the radar, it's going towards the radar, it hits the radar, and now it's going away from the radar. So, we can assume that this wind is easterly, or coming from the east. So, yes, wind direction easterly. Then, again, we start and see where the wind velocity is going towards the radar. So, it's going towards the radar, it's going towards the radar, hits the radar, it's going away from the radar. So, it's northwesterly. So, which velocity plot has the highest wind speeds? This plot has brighter colors, so it has higher wind speeds. So, panel A has the higher wind speeds. Okay. This should be the last PowerPoint for today. So yeah, we just talked about how the radar works, and it sends out a beam of energy, which is called a pulse, and then it's scattered by the precipitation, and some of this energy is scattered back towards the radar, and that's called an echo. And then the radar receives this energy, and it uses it to tell us about the particles in a volume. So it can tell us about the size, shape, composition, distance from the radar, etc. And radar reflectivity is how much energy is returned to the radar. So that's like your classic radar map is reflectivity. But then we also talked about the velocity maps, and this is how fast particles are moving toward or away from the radar. And we said that green, or in some instances blue, mean the winds are moving radially towards the radar, and red means it's moving away from the radar. And the brighter the colors are, the faster the winds are moving. And it's related to the wind speed because the particles usually move with the mean wind. Also, you have to know where the radar site is to determine what direction the winds are moving. Okay. Alright, so elevation is the angle above the horizon at which the radar dish points and emits radiation. So, radars are useful when the beam is within 10,000 feet of the ground, because this is where most weather occurs, like within 10,000 feet. And the elevation angle is also referred to as the tilt. So they will go up and, they'll send out a beam at this angle at 0.05 degrees, and then they'll continue to increase the tilt so they can get the full scan of the atmosphere. So it's spinning around in the golf ball, and it's changing tilts. So the azimuth is degrees around the radar, so it's kind of like a circle surrounding the radar, and the total degrees is 360 degrees. So it's the same as just like a circle. So this radar is spinning in a circle. Radars can rotate the azimuth to be able to scan areas of interest. So the elevation angle determines the type of weather features that can be sampled by the radar beam. So shallow features far away from the radar may completely be missed by low elevation angles. Yeah, so even if you put it on the lowest elevation angle, 0.5 degrees, once you get too far out, this is moving up in the atmosphere. It's not at a perfect flat plane. It moves up because it's angled, so it can completely miss storms that are too far away from the radar site. So let's compare two different radar returns from two different radars at the same spot. White star. Okay, so this is where the radar is. So there's two. Okay, they're at different. Okay, they're kind of close. Okay. Oh no, they're on the same spot, supposedly. Okay, yeah, both radars are at the same spot. Okay. Huh? Okay, KLTX is down here. KLTX is down here. KTLX. Sorry. I'm trying to figure out what she meant by this. So, yeah, I guess, here is the KTLX, and it's trying to scan this storm up here. So, yeah, let's say that the KTLX is trying to... Okay, we're scanning for the same spot, so we're trying to get the storm at this star. So, KTLX is scanning this storm, and it's letting out a radar beam, and this is at the same tilt angle, so tilt 1, so that means 0.5 degrees. So they're at the same angle. But this radar is farther away from this spot than this radar is. So as this beam moves in this direction, it increases in height in the atmosphere. So it's not picking up on this low level precipitation. It's only looking at the upper levels now because it traveled too far. So they put another radar right here, closer to this area, so they could get better coverage. And what do you know? It is picking up the storm in the lower levels because the beam didn't have to travel as far, so it didn't travel as far up in the atmosphere. So KTLX is far from the radar, so the beam is very high, and it's sampling the ice high in the cloud. And remember that, like, snow doesn't really show up as well on the radar as rain. And then KVNX is close to the radar, so the beam is low, and it's sampling the rain that's hitting the ground. The elevation angle determines the types of weather features that can be sampled by the radar beam. So tall features like thunderstorms can be intercepted by the radar beam, even at great distances from the radar. Because they're tall, each elevation angle, including higher angles, will capture a different part of the storm. So this gives us great detail about the storm. So there's two ways a radar can scan precip. So the first way is that the radar moves and scans up and down the elevation and does not move side to side in the azimuth, so it will stay stationary, and then it will just scan up the storm. And then the range height indicator is the display of radar returns from multiple elevation angles, all pointing in the same direction, i.e. the same azimuth. So it's like a cross-sectional cut of the storm, and it's a little confusing why they put this in here because they don't use this operationally. This radar beam is always spinning. Yeah. Okay, the second way is that the radar moves in a full circle at one elevation, and it repeats this at multiple elevation. So the PPI, the planned position indicator, is a display of the 360-degree reflectivity at a single elevation angle. Yeah, so sometimes if there's thunderstorms, they will put the radar in certain storm modes, like VCP 212, or like VIPS or something like that. So what it will do is it will scan like the lower levels multiple times instead of just immediately going up the atmosphere like normal. And it will like wait for certain thresholds to be met before it leaves this mode. So it's able to really hone in on the lower levels where tornadoes might be forming and not waste any time going up the atmosphere. So the geometry of a radar beam means that data are actually collected in a cone-like shape, and it's collected in discrete path regions along the beam's path called range gates. So, yeah, the data are collected in discrete, range gates. Okay, so the data within range gates on the cone is projected down a 2D surface, so we see it as a flat map. So, yeah, it sends a beam out like this, but it puts it down into a flat map. So, the data collected closer to the radar are lower in altitude, and the data collected farther from the radar are higher in altitude. So, when you look at a reflectivity map, when it's closer to the radar, it's lower to the ground, and when it's farther out, it's at a higher altitude, but it's pushed down onto the same 2D surface. So, radar scans the full 360 degrees around the radar at one elevation, so one tilt angle, and then after completing the full rotation at this elevation angle, the radar dish will tilt upwards and then scan the next level of the atmosphere, and then it will just continue. So it does a scan at the lowest level, and then it changes height, and it scans again at the next level, and then it changes height, and then it scans again, and then it goes back down to the lowest level, and it just does the same process. So by performing multiple PPI scans at multiple elevations. The radar scans an entire volume of the atmosphere around the radar. So this is called a volume scan. So once it starts at like the lowest 0.5 and then it goes all the way to the top of the atmosphere, this full thing is called a volume scan. And it can take like 5 to 10 minutes to finish a volume scan. So a PPI is the most common type of radar display. So it's looking down on the weather features from above. It lets us investigate precipitation in the horizontal. So on public radar displays, the news, etc., we're usually looking at the PPI from the lowest elevation scan. Yeah, so this one right here, the 0.5, it sends out this beam and it comes back, and then that's what's displayed on this radar site. Usually they use the lowest level. Okay, here's an important and weird feature. It's called the cone of silence. So they usually don't collect data within the first 2 kilometers around the radar, and it shows up as an empty ring around the radar in a PPI. It's not this. I don't know what this video is. If you want to find out, you can clear. Like you can see, it's just not far enough or high enough off the ground to see anything until you get far enough out to hit clouds. So that's why there's like a cone of silence. It's got to get high up enough to hit the clouds before it can return anything. The WSR-88D radar network. So the U.S. government, specifically the National Weather Service, owns and operates over 140 weather radars across the United States. And they're called the Next Generation of Weather Radar, NextRad Network, which is kind of funny because the reason why it's called 88D is because they were made in 1988. So they're really not the next generation of weather radars. We've been using the same ones since the 1980s, but the individual radars are called the WSR-88Ds, D standing for Doppler, and WSR, I think, stands for Weather Service Radar. Yeah, Weather Service Radar, 1988, Doppler. So these individual radars typically have a protective dome over them called a radome. I just call it the golf ball. There it is. So a volume coverage pattern of VCP describes how the radar dish scans in both azimuth and elevation. So the number of elevation angles scanned and what elevations are scanned. So all VCPs use the same lowest 5 elevation angles. And to do these scans, it takes 4.5 to 10 minutes, and the more dangerous the weather, the faster the radar performs volume scans, so we can get faster updates. So like I was talking about, the radar, like in a severe weather situation, the radar will spend more time on these lower level scans, and that's just so we can get information about surface features faster, because tornadoes don't form aloft. Usually they form at the surface. So that's really where we want to get our information about, so they will spend extra time in this mode where they're scanning the low levels. Clear air mode. So this is just regular mode when there's no precip in the area. They only scan the lowest 5 elevations used because they don't need any more, and it takes 10 minutes to scan. And there's not really a need for fast updates, so it takes its sweet time. And usually in these, you can get bugs, dust, and pollutants. So I have a friend that's doing a project for his master's thesis in Houston, Texas, and he's sampling air pollution out there, which apparently is pretty significant, and seeing if it can contribute to storm formation. But yeah, radars can pick up like bugs, dust, and pollutants. It can also pick up cars and stuff like that. So that's usually what's picked up when you're in clear air mode. Example 2 is a precipitation mode for light to moderate precipitation. So when there's taller non-severe storms and precipitating clouds, it will increase the number of elevation scans to 9 elevations. So as you can see, it's not going as far up here. This is the height above the ground, and this is the range. But when you switch to the first storm mode, it includes these scans that go higher up in the atmosphere. It misses parts of the upper level storms. Like when you're close to the radar site, it can't hit this area. So this is kind of like, this is the cone of silence right here. As you can see, like if a cloud doesn't form until like 10,000 feet or something, like you're gonna have a cone where there's nothing detected. Especially like a mile within the radar, you're really not high enough to get storm coverage. Yeah, the volume scan takes about 6 minutes. It doesn't need to be super fast because it's not like really critical, but it will speed up the radar just so it can get these scans in enough time to make sure that nothing's happening. And it usually samples light to moderate rain and non-severe storms. And then this is VCP 12 or 212. So this is the mode I was talking about. So this is precipitation mode for severe weather. So when there's tall, severe storms, it will scan all 14 of these elevations, and there's no gaps at the higher level. It's sampled as completely as possible, so it will actually scan these lower levels several times. So it will scan the 0.5, and then it will scan the 0.5, and then 0.9, and then it will go up, and it'll go back down. So it'll do multiple scans of this 0.5. And it is, it doesn't leave like very much room for error. It tries to scan it very quickly. In 4.5 minutes, it does this. And the reason why we don't do this mode at all times is because it's incredibly taxing on the radar. Like, it's old technology. They don't really make radar parts that much anymore. So you don't really want your radar to break. And if you're in this mode all the time, it's just spinning really fast and moving up and down really fast, and it like wears down on the technology. So usually we'll stay in clear air mode unless we need this. And this is an automated process. Like, it will go into VCP automatically if it detects parameters for severe weather. So limitations of the radar include ground clutter and non-meteorological target. So close to the radar, where the beam is still close to the ground, it encounters trees, buildings, hills, and other landforms, and this is called ground clutter. Reflect energy back to the radar, but it stays stationary. It's not it's not a storm because it's not really moving around. It kind of stays in the same place. And it can also be reflected back in targets by the air that are not precipitation, so birds, bugs, dust, chaff, etc. They all reflect energy back to the radar, and they move in time, and they move with the prevailing wind. And here's a video of some ground clutter or something like that. Yeah, in my opinion, wet cars are like the worst. Like, if you have wet cars, they look like pretty good storm targets, but they're not. They're just wet cars. Okay, so there's this thing called ducting. So if the temperature increases with height, like if you have an inversion, the radar beam can be bent back down and hit the surface, so it can miss weather features that are above the inversion, and it can hit structures on the ground, which increases the ground clutter. So yeah, ducting, it just happens when there's an inversion that bends the beam down. And it also, like, if there's like something here, usually in an inversion there's not, but if there was, like, it would make it look like these houses are like higher up in the atmosphere or something when they're not. If the temperature increases with height, the radar beam bends back down. So yeah, you can see it here. The beam is bending back down and it's hitting surface features. And then they miss the weather features that are above the inversion. So they just hit the ground structures, and it increases ground clutter. So yeah, this is I-55 and I-75, so you've got these cars, and it's just hitting these vehicles that are moving on this highway, and creating clutter on your radar. Okay. Earth's curvature also creates limitations, yeah, the Earth's not flat, unfortunately. Again, I really wish the Earth was flat, but unfortunately for all of us, the Earth is round, so it creates difficult math problems and also messes up our radar scans. So as the beam goes out from the radar, the Earth is curving below it, so it causes the beam to sample precipitation higher in the atmosphere than it would with a flat Earth. So this causes problems for shallow precipitation far from the radar, yeah. So, I mean, if this was flat, you could measure all of these storms pretty well, but since the Earth is curved, unfortunately for us, the precipitation can be missed because the Earth is curving beneath the beam that's in a straight line. Also, tall obstacles can completely block radar beams, and this is like a big problem in the Rocky Mountains, and it's a problem for the low elevation angles, which are kind of important because that's where a lot of the storms form. You can get the higher elevation angles and they're pretty much fine, but the lower elevation angles, usually they'll just hit a mountain and send the beam back before hitting any clouds. Yeah, here it is. You can see the big missing triangles that of energy that was just like absorbed by the mountain or incorrectly scattered back. So yeah, it's the most common problem in the United States is the blockage of the beam by mountain ranges and especially at the low elevation angles. The radar beam is 1 degree wide in azimuth and 1 degree tall in elevation. Yes. And then, therefore, the range gates in the radar collects data that are much... Therefore, the range gates in the radar collects data are much wider. Okay. Basically what happens is you start out and you have like this 1 degree difference, but as you travel outwards, the little circle that it's sampling gets bigger and bigger, and so the resolution isn't as good the farther out you get, and like the spatial resolution, so meaning like it can't tell where things are as well farther out than it can close, because it's more precise when you have like this smaller beam than it is when you have this large beam that covers a larger area. So it's like the radar sends us out and it's like, oh, it hit something in this small circle, so it must be within this small circle. But as the circle gets bigger, it's like, oh, it could be anywhere in this large circle. So yeah, the spatial resolution's not as good farther out. Okay. Yeah. Yeah. Yeah, this is the same information on this slide. Yeah, so, but we'll look at this image here. So, close to the radar, like, you can see this pixel size. Like, this is the radar. And close to the radar, it's these tiny little pixels, and, like, they're pretty precise, and it can show, you know, oh, there's a small cloud features that are different. But as you get further out, you get these big chunks, like the volume scan is larger. So it's less accurate out here spatially than it is right here. So this has more precision than this. So, also another limitation is sunstrobes. So, when the radar beam is pointed directly at the sun barrages... Is that how you pronounce it? Barrages? I think it's barrages. That sounds kind of French. The sun barrages the radar with energy the entire time it is listening for returns. So the radar thinks that there's lots of precipitation at all range gates since it's sampled high power from all range gates, so it'll look like a spike on the display. So the sun lets out the whole spectrum of electromagnetic radiation, and one of those is microwaves. And so when microwaves are hitting the surface of the radar, it can't tell the difference between the radar that is sent from, like, originates from the radar and microwaves that come from the sun. So it will just think it's a big blob of something in the sky when really it's just the sun. There is the sun strobe. So the sun is over here and it's pointing towards the radar and it's creating this, it's like at sunset, like it's picking up the sunset and it creates this long beam. So the sun barrages the radar with energy the entire time it is listening for returns, and the radar thinks that lots of precipitation must exist at all range gates since it sampled high power from all range gates, so it looks like a spike on the display. Okay. That will be all for Thursday, so thank you for watching my lecture. Email me if you have any questions, and your quiz will open up on Monday.